Oh, that will be good. It's okay. What are you doing? Yeah. Okay, so we are very happy to have Anindya here today. He's frequent visitor to the department. Everyone knows him. He's at UPenn. He's a professor in computer science there. He works on a lot of different areas, but maybe one theme I can say is applying analysis to problems in complexity and learning. So today we'll be telling us about sparsifying the
Thank you. Thank you for having me here. I love coming to Mumbai. So, and apparently, I have still many places to visit, so I'll keep coming back. And plus, I know of this place now, Crawford Market, where if I need anything legal or otherwise, I can come. Okay, so
YouTube. You're being recorded. You're on YouTube.
I have never done anything illegal. Okay, so this is some joint work on with Shivam Nadipali, who used to be a PhD student at Columbia, and I was a postdoc at MIT, Ryan O'Donnell and Professor Radio on sparsifying suprema of Gaussian processes. So,
Just click. No, click. Yeah.
no. Okay. So first, let me start with one motivation. We'll first start with some motivation for this problem about the problem of sparsifying convex sets. Then we will connect this problem to sparsifying suprema of Gaussian processes, and we'll talk about the main result and some consequences, and only just give a little bit of discussion of the proof, but not more. Mostly I'll the proof. Okay. So actually, the initial question doesn't start in the Gaussian or the continuous world, but in the discrete world. And this is a problem, a basic problem in concrete complexity theory about CNF sparsification. Okay. So what is CNF sparsification? So let's just recall what CNF formulas are. So CNF formulas are very central to modern complexity theory, or ancient complexity theory also. They're just basically ands of ORs of literals. So here is an example of a CNF formula on 11 variables, of which most are not being used, but it's basically an AND over terms, AND over clauses, where each clause is an OR of literals. Okay. And there are two measures of complexity or size of two measures of complexity of CNF. One is the size of a CNF, which is just how many ORs are involved, so how many clauses are involved. So in this example, there are 3 clauses. And the second is the width of a CNF, which is look at the clause with the maximum number of literals involved. So in this case, the width is 4 because the first clause has 4 literals. Okay. And a first folklore observation is that if you have any CNF with bounded size, meaning the number of clauses is limited, then with small error, you can also assume that its width is also finite, small. Okay, precisely the theorem is that if f is any function which is representable by a size as CNF, but no gap, the widths can be very long, then what you can do is that you can come up with another CNF f prime, which is epsilon close to f for any parameter epsilon, where the width of f is only logarithmic in your error parameter and the number of clauses. Okay? So in other words, we are saying that CNFs with small widths are essentially narrow. Okay? And here, when I say epsilon error, we are just measuring the change with respect to the uniform distribution. So we're saying f and f prime agree everywhere, but at most epsilon fraction of the places. The proof of this is super simple, really. Just look at all the clauses, and any clause with more than log s over epsilon, just discard it. What this will do is that you are dropping constraints. So the function it will only become 1, potentially become 1 at places where it was earlier 0. On the other hand, the point is that each discarded clause is very long, meaning it was because the clause was very long, it was with more than log s over epsilon, means it became 0 only with very small probability, only epsilon over s. So if you just do a union bound over all your s clauses, this results in a total error of epsilon. This is just folklore observation. And you can now ask, okay, so small CNFs are essentially narrow CNFs. What about the other direction? Are narrow CNFs essentially small CNFs? Okay. So the first answer is yes, there's an obvious thing. If you know that a function is computed by a width WCNF, okay, then it can have at most only n to the w clauses, because if you have only w variables, then only n choose to w times 2 to the w possibilities. So of course, narrow CNFs are small CNFs if you want to involve an n factor, with WCNFs are at most have n to the w clauses. Okay, because those are the possibilities. But this seems to be a little bit of an overkill, because the main thing is that it seems like this, if you're allowing for small error, you might be able to get rid of this dependence on n. For example, if I tell you that the width of W is 1, that is, it's an and of only one of, literals really, then you can, after, if they're more than log 1 of epsilon clauses, then it's epsilon close to the zero function. Okay, so you can just, you can go with one clause, with one CNF is epsilon close to a constant function. Okay, if the number of literals if the number of clauses is more than log 1 of epsilon, so you can say with one CNF can always be approximated by a CNF of size log 1 of epsilon. Okay. So the statement, the question we now ask, the question one can ask in this vein is every width WCNF epsilon close to some other CNF f prime whose size is only dependent on the error parameter epsilon and the width parameter W, no dependencies on n. Okay. Such a statement is called a CNF sparsification result. So you want to say, if you have narrow CNFs, can you sparsify the CNF, not have given any terms? And this actually has been asked and answered. Okay, so the very first recorded result along these lines was a paper from 2004 by Trevisan, who showed that you can get some result. It was actually not a very difficult, it was a simple argument where he showed that with WCNFs of error, with WCNFs can be approximated to error epsilon using 2 to the W to the 2 to the W log 1 of epsilon clauses. Okay, the dependence on W was doubly exponential and the dependence on epsilon was a polynomial dependence. It was a simple packing covering argument. The parameters were significantly improved in the subsequent work by Gopalan, Mehta, and Reingold. And then using significantly heavier machinery from switching lemma, ideas of random restrictions, and some other ideas originating from sunflower improvements on the sunflower lemma. I'm not completely familiar with this technical ingredients here. Basically, in 2021, the optimal dependence was obtained. So it was shown that any width WCNF up to error epsilon can be approximated by essentially 1 over W log 1 over epsilon to the order W clauses. So we see that dependence on the epsilon is now just logarithmic in 1 over epsilon, which is essentially tight because even for the width 1 case, you needed log 1 over epsilon. And the dependence on W, in terms of at least the dependence on log 1 over epsilon, is just exponential in W. So it's log 1 over epsilon to the order W times 1 over W to the order W. So this is the optimal thing that can be done.
So this is what also is the same paper will give rise to better bounds for the sunflower lemma?
I think the other way around. The sunflower lemma came first, and then as many of these arguments were adapted. I'm not entirely familiar with the technical thing, but I think that sunflower thing proceeded this way. Okay. But this was we are not going to do anything about with CNFs and all this. This was just setting up the stage for the question. Okay. So now, so for the last several years, actually, with Shivam and Rocco, we have been thinking a lot about analogies between Boolean cube and Gaussian space. Now, of course, at a technical level, we know there are these things like invariance principles, which allow us to go from the Gaussian world to the discrete world on general functions, obeying certain conditions. But this is slightly different. In particular, we have been trying to understand how discrete structures can be related, how discrete structures, especially things like CNFs, can be related to convex sets. Okay, studying Gaussian convex sets over the Gaussian space and study that as an analog of CNFs over the Boolean cube. Okay, there is again I'm going to essentially discuss this analogy a little bit. But point is, unlike the invariance principle, there is no transference theorem we have. We just have many, many points of correspondences that we have seen so far. So I'm not going to go over all of them, but just going to maybe you look at this example. So in particular, here's what we're interested in. We want to know the sparsification of CNS over the Boolean cube. Is there an analog of this kind of a result over the Gaussian space? Okay. So the uniform distribution is going to get mimicked by the Gaussian space, but we have to ask, what is the analog of a CNF over the Boolean cube? Okay. What is the analog of a CNF over the Gaussian space? Okay. So let's try to it's an analogy. So let's try to come up with a plausible correspondence. So what does what does a clause do? A clause basically chops off a part of the subcube of the hypercube, right? It basically chops off a subcube. For example, the clause if you look at this clause x1 or x2 not or x3, it basically says this particular pattern, which is 0, 1, 1, is forbidden. That's what a clause does. It says this is forbidden. And what is the analog of chopping off a part of the space in the Gaussian space? Well, so one particular thing could be think of something very simple, like a half space. A half space also says chop off a part of the Gaussian space, much like a Boolean, but like a clause says chop off this part of the Boolean cube. Okay. A little more here, maybe. So, what is, for example, a clause of width W chops off 1 over 2 to the W fraction of the hypercube. In the Gaussian space, because all half spaces are created equal, if I consider a half space of the form u dot x less than equal to W, where u is a unit vector, then to chop off a half space of width W would chop off roughly e to the minus W square over 2 fraction of the space. Okay, just like this is just a bound on the Gaussian table. Okay. And okay, so some useful analogy for later will say that a half space is of width geometric with W if it is of this form. Okay, any half space can be written like this. Any half space can be written as u dot x minus W less than equal to 0. Okay, so if you normalize so that the vector involved is a unit vector, then this W can be specified now, and we'll say it has geometric with W if it's written in this. Okay. So basically, the boundary is like W away from the origin.
But you're allowing W to be negative also. No?
Yeah. I'm allowed. Well, no, I don't have to allow W to be negative, right? Because in this form, I can always say U dot the inner product is less than equal to. So I'm typically going to consider. Okay, we'll come back to this. I'm typically thinking of it as positive.
What's the plus minus bit?
Use just an arbitrary unit vector.
But you always think of cutting off the smaller part.
You're cutting off the smaller part. We're not cutting off the larger part. I mean, the question we're going to think about is we're going to cut off the smaller part. Yeah, W is positive. Okay, so now recall what we were talking about. So we're saying in the Boolean cube, we saw that every Boolean function can be expressed as a CNF, okay, where we have to allow clauses of arbitrary width, not really arbitrary, the width can be at most 10, and you have to allow as much as 2 to the n clauses, okay. So similarly, what would be the analog in the Gaussian world? You will say every convex set over R to the n is expressible as an intersection of half spaces. The number of half spaces you might be like infinite, uncountably infinite. And the half spaces are allowed to have arbitrary width. But every convex set can be expressed in this manner. Okay. So CNFs correspond to, maybe the moral of the slide is, in this analogy, clauses correspond to half spaces. The intersection of clauses correspond to intersection of half spaces, which is just a convex set over R to the n. That's the moral of this thing. And we will say a convex set K has geometric with W if it's an intersection of half spaces of geometric with at most W. Okay, so we're thinking of a convex set with the origin contained inside it. Okay.
Final statement is not clear.
Sorry?
The final statement.
This one? Yeah. Oh, this is a definition. So I'm saying we will call a convex set. So every convex set can be expressed as an intersection of half spaces. And we're thinking of a convex set which contains the origin. Okay, so now we're cutting off, like, I can think of like an intersection of many half spaces, which are defining this convex set, and the width is W if no, if if all the half spaces have width at most W.
But then you have to have something smallest possible, something
Um,
somewhere it has to come in.
Intersection and causes.
No, yes, it's the smallest W. It's the smallest
It's the smallest W. Sorry, it's the smallest W. It's like it's the smallest W, or it's the smallest W. It's the size of the largest ball you can fit in. It's a largest ball you can fit in. It's like the ball of width W completely. The largest W such that the ball of radius W, like, yeah, absolutely. The ball of the W, the largest W is a ball of radius W, like, completely. Okay. So, like, you're thinking of this as the geometric width, analog of the geometric width. So now again, okay, so what do we know about? So now what do we want to do? We want to say, earlier we said that in the CNF world, we had said that if a CNF has bounded size, first the folklore observation is that the CNF had bounded size, it has bounded bounded width as well. So now we can first say, okay, what is the folklore analog of the folklore observation here in this world? So let K be an intersection of half spaces, S half spaces, only S half spaces are involved. Then you can also find another intersection of half spaces, which is epsilon close to K, okay, which has geometric width at most 2 square root log S over epsilon. And here now, when we're talking about convex sets, we're measuring distance vis-a-vis the Gaussian measure. So saying take any convex set, which is intersection of S many half spaces, then it must be close to another convex set, which is an intersection of much fewer half spaces where it's an intersection of half spaces with only small width, okay, where the width depends only a square root of the log of the number of half spaces and the error. Yeah. And this is again exactly the same argument as before. If you have a half space which is very wide, just drop it, because that is cutting off only a small part of the Gaussian space. So just apply a union bound. And now instead of log S over epsilon, we're getting square root. That's because the Gaussian density has a e to the minus W square as opposed to the Boolean thing at 2 to the minus W. So that's why we're getting this.
So you say epsilon close to K, that every point on K has a nearest point.
No. So good. So let me, when we are saying two convex sets are close to each other, the Gaussian, we are saying this I should explain more. I'm saying that Gaussian volume of the symmetric difference is at most epsilon. Right. So there are many ways to measure approximation in Gaussian, in the Gaussian world, what you're referring to Hausdorff distance. So we are measuring it according to like this Gaussian L1 measure. So look at the difference between these two bodies. What is the L1 Gaussian measure of that set? Okay.
Like in the Boolean case, this sparsity and the width, right?
Right.
They are sort of related.
Right.
That's not the case over here.
No, that's what we're trying to build up the case to be here.
Yeah, I mean, so like.
So Boolean case, we showed that if the number of clauses is S, then you can assume that the width is no more than log S over epsilon. In the converse direction, the list of results I said is that if the width is no more than something W, the number of clauses is no more than basically W to the W.
Yeah, I mean, so like, I guess what my question was that this new intersection, right? K,
Yeah.
This new convex body, let's say K prime, right?
Right.
So like, I don't know, like, maybe you have this answer later on in the talk. So do we have a bound over the number of like half spaces needed to bound this body?
Well, so we're starting with the hypothesis that K is an intersection of S half spaces.
Yeah, but like we already know the
new half. Oh, sorry. So the new intersection of half spaces K prime.
Yeah.
That has also at most S half spaces.
Okay.
And the width is also small. And then, the statement doesn't say this, but the proof says this. Basically, the proof is just drop the half spaces which are very which are very wide. That way, you're not increasing the number of half spaces because you're dropping constraints. But the error you suffer in this total process is at most epsilon.
Yeah, I mean, yeah, that makes a lot more sense.
Yeah.
Another question.
Yeah.
You're starting with K being an intersection of S half spaces.
Right.
You're not assuming any geometric with bound on K.
Yeah.
But then why should log of S appear instead of the
Decide whether to keep it or.
So every half space, so exactly like what we did in the Boolean world. In the Boolean world, I said, I have S clauses, no guarantees, no requirement from the width. Then I can get something which also has at most S clauses, but now the clauses are also narrow because I just drop the ones which are very long. Here I'm saying, take the half spaces, the ones which are very wide, just drop them. Because if you had only S half spaces, dropping the very wide ones do not cause a big error. So now I want to ask a converse, okay? Based on light of all this, that suppose you had an convex set which is a geometric with W. So you're saying, okay, so excuse me. So you're saying basically you're saying the largest ball that can be completely contained inside this set is of with something, some constant, let's say. Okay. Does it mean that this such a convex set can be approximated by an intersection of half spaces whose number depends only on the width and the error, no dependence on it? So exactly like, given like, we have the folklore observation in corresponding to the Boolean world, we now want to see whether all the works I mentioned earlier, whether that can be analogized in this setting also. Okay. So if you have a convex set, you can put the largest ball you can put in is relatively small. So it means like in any direction then does it mean that you can also approximate such a convex set with very few half spaces where the number only depends on the width and the error. Yeah. So sorry.
Yeah, I have a question.
Yeah.
Can you just restate this epsilon closed definition once, right?
Yeah. Can I write on the chalk? So for any set K and K prime in R to the n, the distance, let's just say, between K and K prime is the probability that when you sample from the standard Gaussian measure, it falls in the symmetric difference of K and K prime. So saying like, look at every point which is in exactly one of K or K prime, but not both, that's a very small quantity.
Yeah. So now this discarding half spaces sort of makes sense because, otherwise it.
Yeah. So like, I'm just saying discard those half spaces, then you're getting.
Off here, the scaling is bothering. So what if we just squeeze the body down and reduce to it?
Opening the thing.
no, there's epsilon.
Yeah.
So if you
Gaussian distribution.
the distribution is not invariant. If you squeeze the body, if you take a body of certain width and you just say I will make it like squeeze this, then the volume just rapidly will change. The volume will shrink very quickly.
Yes, but if I approximate this thing with half spaces, the same number of half spaces I can stretch.
But this is an additive approximation. So for example, suppose you
decrease if I stretch.
So you start with your body, okay, K. Now you're saying, okay, I scale down this body. Okay, I have a new body, let's say K1. I approximate this body with another set. The error there is epsilon. Now you stretch that body up, but then the error could blow up really badly.
Yeah, because what you're saying would be multiplication wise, but as you said, the error is in the additive, right?
So maybe just an example, if I consider the ball, okay, in the Gaussian space, to have a constant volume, you need width root n, that would be the ball. Okay, if I decrease it by 0.9 root n, the volume of the Gaussian volume of the ball is now basically 0. So I could just say, 0, the empty set is a good approximator here. If you scale back the empty set, you just still get empty set, but now the error will just blow up to half. So this, because this is unlike many. So this I would say, like, maybe we are not going to discuss the other error metrics, but at some level the L1 error metric is useful, of course, from the point of view of computer science, because we measure errors and many things like that. But it is sensitive to scaling things. It is like, the Hausdorff distance, etc., is much more benign in the way it behaves with respect to scaling, or the many other metrics that are studied. But this is like very sensitive. You stretch the body up and down a little bit, things can become completely trivial. So question we're asking is, the body has bounded geometric width. Does it mean it can be sparsified in this manner? Okay. And the answer is yes. So eventually, like we eventually proved that this can be done. The dependence on W is doubly exponential, and the dependence on epsilon is also our dependence on W and epsilon is both doubly exponential. Okay. So we actually first tried to, like, basically, obviously, like, given all the background that was there, and uh, like CNS classification, the idea was, okay, we should be able to do something, just analogize those things, like, do the corresponding things over the Gaussian world. So we first started obviously with the simplest argument, really, to get something from this paper by Trevisan, but we couldn't make it work really. And so eventually, like, we moved to, like, using this ideas from, like, basically not just ideas, but basically the proof uses the majorizing measures theorem. Okay, from this very central theorem in the theory of Gaussian processes. Okay. One could ask, like, I would maybe touch on this later, but I forget when it is in the slides. One could ask, okay, like, is this too much of a heavy hammer to be used for a potentially problem which could be solved in another manner? Like, I mean, just because we couldn't make it work doesn't mean it wouldn't have worked. And one thing is that we can prove that an exponential dependence on W and an exponential dependence on epsilon is necessary. Okay? Whereas if you remember the Gauss CNS classification results, the dependence on epsilon, is logarithmic there. And here an exponential dependence on epsilon is necessary. And I think, sorry, what am I? And the dependence on W there is singly exponential. I think you can prove there's a doubly exponential dependence is necessary. So anyway, like, there is like some gap between what we can prove in the upper and lower bound, but it seems like some of that stuff cannot be maybe replicated, because there are quantitative things which can, qualitatively we can achieve the same result, but not quantitatively. Okay. So we prove this result, but we'll prove this using the theory of majorizing.
But sorry.
Yes.
If I just wanted to prove that the ambient dimension doesn't come in,
Yeah.
then is there a simpler way?
No, we were just trying to prove some ambient dimension. We were just like, let's just get some like triply exponential dependence on epsilon and something.
N should not come
We
in.
just n should not come in.
Yeah.
We couldn't make it work. And we tried all sorts of arguments really, and thought, oh, this should be like, eventually when we finally got this proof and then we were trying to get lower bounds, we also realized like the kind of upper bounds that were achieved, even in Trevisan's first paper, are not simply achievable here. So there is, might be like, that there is no simpler proof. This is what you have to do. So what I'll now do is like, okay, this was the background. I'll now talk a little bit about like Gaussian processes, majorizing measures, what does it mean, what does it do, and then try to like come back to why does it relate to this problem.
So suppose you just dirty the entropy integral, do you get some weak dependence on n?
Sorry?
If you dirty the entropy integral, which suppose is a weaker analog of this majorizing measure technology.
Yeah.
Do you get some weak dependence on n?
I don't think so. Do we get some weak dependence on n?
You wanted independence on n. Probably.
Yeah, we wanted independence on n. It's a good question. Like, could we get a non-trivial? Okay, so I mean, we have the width and we have the dependence n. So by a weak dependence on n, we mean something like log n, something.
Log n, I don't know.
Root log. Okay, good question. I don't know. Like, I don't know the answer on the top of my head. I do not know. Like, we could have gotten some weak dependence without using like the full Talagrand majorizing measurement. Maybe I don't know the answer really. Okay, so I'll just recall like what are Gaussian processes. So what are Gaussian processes? Basically, a set of any real random variables is a Gaussian process if any finite linear combination of these random variables is a Gaussian instance. Okay. And in this talk, as is much of like Gaussian process theory, we'll only consider centered processes, meaning every random variable has mean zero. Okay. Now, there's a notion of, I mean, if we, okay, like, I mean, we don't lose significantly if we just think this set T is finite or countably finite. But anyways, like, since we have to think, like, just to have a little more formal definition, one way of realizing a Gaussian process is that you consider a set of vectors Vt, okay, and in R to the n, in some L2 space, let's think of the space as n finite dimensional R to the n, okay. Now you sample a Gaussian, n-dimensional Gaussian, standard Gaussian in the space, and then the the xt variable is defined as the inner product of G with Vt. If you have this kind of a definition, this gives rise to a Gaussian process, because you take any finite linear combination of xt's, you will again get inner product of G with some other vector that's still a Gaussian. So this is called a canonical Gaussian process. And a fundamental thing is that if the set T is countable, then any centered Gaussian process can be realized as a canonical Gaussian process. And in our case, we will just focus on the case when T is finite. Like, we don't have to really think about the case T equals infinite, because you can always, like, first do some basic argument to just show T can be finite even if exponential in n, T can always be assumed to be finite. So we'll just focus on the case T to be finite, or in other words, we can just think about canonical Gaussian processes. Okay. Oh, sorry, I didn't say what T was. So I'm thinking, like, when you're considering intersections of half spaces, you can always assume the number of half spaces is at least finite, because, you can finite but exponential in n, because you can just drop a few of the half spaces. So we'll just have to think about finite Gaussian processes. Okay. And so the nice thing is that once you think about canonical Gaussian processes, the random variable is in one-to-one correspondence with the geometry of these vectors. Okay, so in particular, because a Gaussian process is completely described by its variance and covariance. Okay, note that the variance of the random variable xt is just the inner product of Vt with itself, so the norm of Vt square. And the covariance of xs and xt is just the inner product of Vs and Vt. So this is like a standard thing, that the Gaussian process, the random variables, it's completely in one-to-one correspondence with the geometry of the vectors. And again, like, this supremum Gaussian processes has been studied very widely, starting with work of Fermi, Dudley, Talagrand, many others, really, many applications. So let me answer this one question. Like, first is, what is the connection between suprema of Gaussian processes and this convex set approximation problem I was talking about? What does these two things have to do with each other? And the answer is really, okay, so let K be a convex set. We think of convex set. Again, we are considering only convex set which have the origin inside it. Okay. So let's containing a ball around the origin, and note that we can write each supporting half space as v dot x less than equal to 1 for some vector v. Need not be a unit vector. I could have either said each of them are unit vectors and then the widths would be different, like v1 dot x is less than equal to w1, v2 dot x is less than equal to w2. Or I can just make all the w's as 1, the right hand side as 1, but now the vectors won't be unit vectors themselves. But I can just say, okay, each supporting half space defining this convex set is of the form v dot x less than equal to 1. Okay, v need not be a unit vector. Now, note that a draw of a Gaussian point, if I draw of the standard Gaussian, falls inside this lies outside this convex set if and only if at least one of these inner products exceeds 1. Or in other words, I can just like rephrase and say the supremum of from T over T, Vt dot G is greater than 1. Okay? So convex sets over the Gaussian space is tightly related to the suprema of the corresponding Gaussian process. You can just say, well, we are interested, the convex set is precisely the set of points where the random variable realization, which is the suprema of Gaussian process, remains smaller than 1. Okay, that is like, the obvious connection, really. There's no deeper connection. This is all the connection. Okay. So it makes sense that we could try to study these sets in terms of these processes and potentially leverage some heavy hammer from that theory, which is exactly what we're going to do. So a few more things. How am I doing on time?
About 25 minutes.
Okay. So we were talking about Gaussian, we were talking about convex sets and then geometric width so far. But when we think about Gaussian processes, there's a very standard object that has been studied, which is called the Gaussian width. Okay. And the Gaussian width is nothing but for this canonical Gaussian process, just the expectation of the supremum of xt. Okay. And again, since we are thinking of xt's as centered, just obvious observation, this is always a positive number because even a single Gaussian process, if it's centered, the expectation of xt is greater than equal is exactly 0. So when you take supremum of various things whose expectation is all 0, you have the Gaussian width is always greater than equal to 0 for any centered Gaussian process. The expectation of supremum is always greater. Okay, this is called the Gaussian width of the process. And informally, this quantity, this expectation of the supremum, controls at some level how complex this Gaussian process is. That's a nice thing because the Gaussian process is defined by this infinite set of vectors in a high dimensional space potentially. The expectation is a single number. Okay, so of course there is a limitation as to how much one single number can capture the complexity of something else. But as we'll see, there's a lot, and a lot of this is known already, of course. But informally, what the single number will it tells you how complex the process really is. Okay, so let's try to get a sense with some examples. Okay, so let's consider two extreme examples. One is, suppose my set of vectors wt are just t orthonormal unit vectors. Okay, then what is the expectation of the suprema? It's actually the essentially theta of square root log of t. Okay, and so if you have t or t vectors which are all orthonormal, then the expectation of the supremum rises in square root of log t. And in fact, one can show that for t unit vectors, this is the maximum the expectation of the supremum can be. It the maximum is when they're all orthonormal, and in that case, it is theta square root log t, and that is the extremal example. Okay. Another one, maybe very representative example is that suppose you have a set of unit vectors. Now I do not stipulate any bound on how many vectors are there, but I just say that they all lie in some d-dimensional subspace. Okay? And think of d as small. So I could have like infinitely many unit vectors all lying on a two-dimensional subspace. Okay? Then what is the expectation of the suprema? Well, it actually turns out to be exactly order square root of d. Okay, because if you think about even if you put the nice thing about the suprema is that if you add more vectors to it, the supremum will only go up really. Okay, so what is the maximum expectation of the supremum you can happen? Well, take all unit vectors in a d-dimensional subspace. Okay, so basically just think of all unit vectors in R to the d. Then the maximum is basically just you just basically look at the Gaussian and look at its width, look at its length really, because you will look at when you look at unit vectors, if you take a draw from the Gaussian in n-dimensional space and then say, I will look at inner products with every single vector in R to the d, it's just like the one maximizing the inner product is the one vector which is aligned in that direction. It's exactly square. This is the elementary geometrical relation. So what I want to say is that if maybe a second example is the same, even if you have many vectors, but they lie in a small dimensional space, the expectation of the supremum is small. However, the first example is also saying if they lie in many directions, so if there's like a big space getting spanned, then the expectation of the supremum will be large.
What is chi-d?
Oh, chi-d is like the chi-square distribution, the square root of the chi-square distribution. This is the length of the Gaussian vector dimension, which is chi-d. So maybe these two examples are just supposed to suggest that somehow the dimensionality of these vectors controls how big this expectation of the soup is. Okay, not the number, but the dimensionality. Now, the interaction could be a little more subtle if you consider a more interesting example. For example, if you consider t vectors, where all of the vectors of the following form, they all have a big component along E1 like square root 1 minus delta, and square root delta of the component is along a new orthogonal direction. Okay? Then what is the expectation of the suprema? You can work this out. And it turns out to be theta of 1 plus square root of delta log t. Okay? What does this mean? This means that if the delta, the number of orthogonal directions we are going to take is at least 2 to the 1 over delta, okay, then the second term will start dominating. The theta 1 will no longer be the case. It will be like the second term will start dominating. So even a little perturbation in new directions could help and give you a big number, provided there are enough of those vectors. So, okay, so some version of what the supremum is depends on not necessarily like dimension in which they lie, but some like combination of dimension, but like, effective subspace. What is the effectively a big subspace that is spanned? Some number is going to play a role. Okay, but more of these three examples just to say it's not really the numbers, it's not really how many vectors are there, it's really the effective dimensionality of the vectors that controls the expected supremum. Okay. And so now, like, okay, so maybe like, with these examples, we can say the following. Okay, it is certainly like, just example 2 itself, this says, if you have a set of vectors which lie in a low dimensional subspace, the expected sup is small. Okay, if your vectors lie in a d-dimensional subspace, the sup will never exceed square root d. So if d is a constant, the expected sup is a constant. We now want to know the following. Just basically converse to this question. Suppose I told you that I have a Gaussian process, so the expected sup is a constant. Okay. In what sense can I say that the set of vectors lie in a low dimensional space? Okay. Can I say that the set of vectors lie in a low dimensional space if the expected sup is a constant? And some version of this, can I say that like, I can, okay, so let me like, there are various answers to this question, and our main theorem gives one answer to this question. Let me just state that theorem. It's saying, let Vt be a set of vectors, no stipulation on what the length is, okay? Some vectors can be long, some vectors can be short. Look at the corresponding Gaussian process. Take any error parameter. Suppose you know that the Gaussian width of the original process is small, okay? Then you can approximate the original centered Gaussian process with a non-centered Gaussian process. So I'm just adding these offsets, okay, such that these two Gaussian processes are close to each other in the following sense. The first random variable and the second random variable are close in, like, if you look at the expectation of the absolute difference of the expectation of the absolute value of the difference, it is small. Okay, so it's saying a Gaussian process with small Gaussian width can be approximated by a Gaussian process non-centered one, which has relatively few vectors. The crucial part is that the relatively few only depends on the number of vectors, only depends on the error parameter. There's no dependence on the dimension. That is the crucial part here. Okay. So this is the thing. S has no dependence on n or t. Okay. So saying any Gaussian process which lies in small dimension can definitely, any Gaussian process which lies in small number of dimensions can definitely has a bounded suprema, but in the converse direction is also true, that any Gaussian process with a small supremum, constant supremum, let's say, can also be approximated by a Gaussian process which has very few vectors and thus lies in small dimensions. The only thing you have to add here is that these are the offsets. They're affine transformation. Okay. Let me pause, try to make sure we are all on the same page here for what's happening.
It's not even like affine. It's not. I can't reproduce.
It's a non-centered process, and you're not just saying that the Gaussian vectors, they lie in you're saying something. You're not saying that the Gaussian process has small width and thus the vectors lie in a approximately low dimensional space. Not just that, they don't just lie in a you're getting a small set of vectors, which of course now definitely lie in the small dimensional space because they're only constant. Like these many vectors can only lie in these dimensional space, and they're powerful enough to replicate the original Gaussian process. Like the corresponding Gaussian process point-wise agrees. It's not that the expected soup agrees. That would be a trivial statement. You're saying this random variable point-wise agrees with the earlier.
Can you remind me again what the W of T is? I mean, it's the width, right?
It's the Gaussian width of the process. So the W of T is the expectation of soup of xt.
So it lies between 0 and infinity.
It's 0 and infinity. You have 0 and infinity, and your error is multiplicative in that sense. Like whatever was like, of course, if you scale up every vector by a factor of 2, the Gaussian width will blow up by a factor of 2. You're saying, okay, so then this one also. So it's basically saying, okay, you start with the Gaussian process. The Gaussian process you start with has to be centered. Okay? It's crucial. The Gaussian process you start with has to be centered. You start with the Gaussian process of any width, let's say million.
But you're not assuming that the vectors are unit vectors.
No. The Gaussian process you start with is any set of vectors. It has some Gaussian width, 100, let's say. Say, okay, fine. I want a multiplicative error approximation, epsilon equal to 0.01. So then I can come up with a subset of these vectors and some corresponding offsets. Okay? Where the number of vectors I come up with only depends on my error, and such that and choose a subset of these vectors plus these CSS, the offsets, such that this new Gaussian process of a much smaller set of vectors point-wise approximates the earlier Gaussian.
Sorry, so in geometrically, what is the Gaussian width again?
Geometrically, so the Gaussian width is so Gaussian width is there is no geometric per se meaning.
You have this convex set. No, it's not anything in terms of
So
convex set.
in terms of the vectors, it's like the largest inner product.
So geometric width was the right. So geometric width,
like because the soup is just soup of Vx Vg.
So they're related, but they're not exactly the same. So if you have a set
expected supreme of the large expected of the
But there are constraints. Those are constraints.
the smallest the expectation of the largest inner product of a random Gaussian with the vectors. I mean, the Gaussian process.
so we are okay. So
xt is just
when you take the sorry. So maybe I can write it. I'll write it, but I won't have it all again. So we are looking at initially when we were looking at the convex set.
no, not the convection. I'm just saying xt itself. I can just think of it in the canonical way. Right? xt is just a vector.
Xt is just a collection of vectors.
No, yeah, inner product is a single Gaussian.
Yes.
So it's like the expected supreme of the Gaussian. I take a Gaussian and take the maximum inner product of the Gaussian with the whole set of vectors.
No, that is right, but I want to think of it in terms of the convex set. Because these things parameterize the constraints of the convex set.
Right. So if you consider a convex set, like okay, so we were initially considering like convex set is of the form we had written it like v dot x vi dot x less than equal to wi, where all these vi's were unit vectors. Now we are saying this corresponds to vi dot x less than equal to wi, or I can say vi over wi dot x is less than equal to 1. I can equivalently say this. And the corresponding Gaussian process then is a soup of vi dot wi dot x's. Okay, that is the so as the geometric width increases, these wi's become smaller and smaller, and then these vectors become larger and larger because each of these vectors has norm 1 over wi. Okay, so the geometric width the geometric width is becoming large. If the geometric width is w, then these vectors have if the geometric not all of them, right? So the geometric width is the maximum the maximum wi here is if the maximum wi here is w, then that means that the minimum vector involved here is going to be at least 1 over w. There are vectors of larger length, but yeah, I'm not sure there's a very direct way. Maybe let's consider a simpler case. Okay, let's consider a simpler case. Okay, let's assume that we are considering a convex set where all the vectors involved have width exactly W. Like, not that the maximum one is width W, all of the supporting half planes have width exactly W. If all of them have width exactly W, then all the vectors involved here have norm exactly 1 over W. Okay? And so now we are saying, suppose a convex set has constant width, let's say 10, then we are saying all the Gaussian vectors here involved here are exactly of length one. All the vectors involved here have length exactly 1 over 10. Okay? But there may be many, many vectors. Okay? And we are saying such a Gaussian process, okay, which have many, many vectors, all of width 1 over 10, okay, could be approximated pointwise by another Gaussian process with some offsets involved, where the vectors actually do not really change. They're all the same vectors, but I add some offsets. Okay, and that supremum that Gaussian process and my new sparsified Gaussian process are pointwise close to each other. And now what we can do is we'll say, okay, let's take these half spaces with corresponding offsets, and because the Gaussian processes are close, we can hope to argue that the corresponding convex sets they define will also be close to each other. To go for this, you request a little more about the random variables, that the random variables, the Gaussian process random variables is anti-concentrated and stuff. So you're not putting too much mass anywhere. Otherwise, you cannot go from a continuous statement to a discrete statement. But that's what's going on. I don't know if I made.
Yeah, so basically these outliers only make the theorem weaker, right? If you have a outlier in the metric space,
Yeah.
they just make it weaker.
Yeah.
So the case you told is the tightest.
Is the hardest case. Yeah. If you have if you have a very long, if you have all the Gaussian, all the process, all the half spaces involved of length 10, and there's one of length 100 really, you can kind of discard it really. It is very long, it's not really adding a big constraint. So really the ones adding big as the width becomes bigger and bigger, right? As the width of the Gaussian process as the width of the geometric width of the convex set becomes bigger and bigger, at some point you're also approaching the constant of one function really. You're saying a big ball can be described. Maybe let me also add this thing that this kind of multiplicative approximation can actually be transformed into a somewhat stronger kind of multiplicative approximation. Namely, if you start with a set of your vectors are symmetric vectors, meaning if Vt is included in your set, so is minus Vt. And when you think of symmetric convex sets, the corresponding Gaussian process is also symmetric, because it's just saying if x is in the set, minus x is also in the set. So if you consider something like symmetric Gaussian processes, then you can get this kind of same parameters as earlier, but you can also get this kind of an approximation. Namely, at 1 minus epsilon fraction of the positions, the old Gaussian process with arbitrarily many vectors can be approximated by this new Gaussian process up to multiplicative error plus minus epsilon. So earlier when we had a Markov kind of statement that the average L1 difference is not very big, now you're saying actually this can be translated in terms of symmetric setting to this stronger multiplicative approximation. This uses some anti-concentration of symmetric processes, which is not true for asymmetric processes. Actually, so another thing is so far we were approximating things with these non-centered processes. When you're considering a symmetric set of vectors, you can actually drop the constants. You don't require these offsets anymore. Okay, you have to do a little more changes. You cannot. Just to give you a comparison between what is going on. Here, the set of Gaussian processes we have is a subset of the original thing. Okay, but some constants are required. You can get the same guarantee, except where you drop the constants, but the vectors are no longer the subset of the original vectors. So you can either add offsets and keep the same set of vectors, or get new vectors but not have offsets. One of these things you can do. You cannot do both simultaneously, but you can do one of these things for a symmetric set of vectors. Otherwise, quantitatively, nothing has changed. Either you add your offset or don't add the offset, but get a new set of vectors. Okay. Maybe one corollary of this thing, which I'll state the corollary. When I asked around a lot of people in convex geometry, none of them knew that this is true. But it's also it's hard to come up with a example which is very stark example. Look what this is saying. But let me first state what the theorem is. Maybe you can tell me if there's something obvious or not. See, any norm over R to the n can be written in this manner. That it is the supremum of V inner product with X, where V is a symmetric set of vectors. Any norm can be written in this manner. It's supremum of V dot X where V goes over symmetric set of vectors. Okay, so if you are if you're looking at the L2 norm, it's V is just a set of all unit vectors. If you're looking at L1 norm, it's something else, and so on.
Dual.
Sorry?
The dual.
It's a dual, right? And L infinity norm is just E1 minus E1, E2 minus E2, En minus En. Okay. And so what the earlier theorem is now saying is that if you look at any norm over R to the n, it can be approximated by a low-dimensional norm in the following sense, that at 1 minus epsilon fraction of the Gaussian space, it agrees with 1 plus minus epsilon error. Let's try to see this in the language of norms. How does this relate to anything else? So all this kind of Dvoretzky's theorem, etc., and norm spaces, etc., says that if you have a norm in R to the n, you can get it get a low dimensional approximation with log n dimensions. Okay. It's weaker in that sense, but it's a much stronger sense of approximation. It's not a probabilistic approximation, those kind of things. Those approximations are everywhere it's approximated within 1 plus minus epsilon. What this is
probably for Euclidean approximation in that dimension, no? You have a slice of that dimension,
right?
That is almost Euclidean. Isn't that what Dvoretzky said?
That is Dvoretzky's theorem. But I thought that it can be rephrased in another manner. Maybe I'm wrong.
No, it can be rephrased. But I thought to do L2 L1 you need almost linear dimension. So if you want
for L1 bond you require
so if you want a subspace of L2 which has where the L1 and L2 are roughly isometric,
I thought any norm
log works for any norm. And for L1 bond you can do much better. You can have very large dimensions.
That's
the dual way.
Oh yeah. So what I'm saying is that you can find a linear.
L1 L2 you can find a linear
dimension, linear dimension.
Yeah, but I'm thinking that doesn't it? I thought it means that if you take a norm over R to the n, I thought it means that it can be rephrased to say that basically you can find a log n dimensional norm which approximates at pointwise up to plus minus 1 plus minus epsilon. Wasn't this true?
No, I think what you're saying is so that's what we are saying is a stronger case for L2 versus L1.
Okay.
What you're saying is so I think translated to this thing, it will become not a linear drop but an exponential drop.
Okay. I think it's true. Basically you can approximate any norm. Yeah. Sorry, I'm not very comfortable with these norms really, but I think basically any norm over R to the n, you can approximate it pointwise by a norm everywhere, which is a much lower dimension, but log n dimension. I think basically it is true. And this is strong in the sense of dimensions, but it's only a probabilistic approximation, meaning you're not approximating the norm everywhere, but only over a large part of the Gaussian space. So basically you're saying every norm, if you look at probabilistically, is close to a low dimensional norm in this constant dimensional norm. It's okay, so couldn't find any proof of this theorem really known. What does it say? Does it imply something super interesting really? I don't think so really at some concrete levels of norms. So for example, if I consider the canonical L2 norm, over the Gaussian space, it's really just constant because most of the Gaussian space, the mass lies in a ball of radius root n. So that if you normalize by root n, most of the Gaussian space, the norm is really almost a constant. You can also, of course, consider some other norm like absolute value of x1 plus x2. This is also a norm over R to the n, but this is already low dimensional. So it's approximated by low dimensional norm because it is a low dimensional norm. And what we are saying is that every norm is basically if it's truly a high dimensional norm in this sense, it actually becomes a constant over the Gaussian space. And otherwise, it is low dimensional, then it's low dimensional. So, okay, so it's not like am I out of time now?
Yeah, maybe 5 minutes.
Okay, let me wrap up in 5 minutes, okay? Let me actually skip exactly how this is proved, like, why, like, this implies all the results and some other things I mentioned. Maybe let me say a little bit about, like, this uh, main theorem, okay? Like, just quickly where the Gaussian majorizing measures theorem comes up. Let me just quickly say that, okay? So this is what I want to prove, okay? I have a set of vectors, I have a corresponding Gaussian process in R to the n. I want to say you can approximate it by another Gaussian process involving few vectors with this kind of an error. How will we go about doing such a thing, okay? So I have a set of vectors I want to approximate and a corresponding Gaussian process defined on it. I want to approximate it by a Gaussian process defined using few vectors. Okay, natural idea is I have all these vectors, I should try to cluster the vectors and say that this vector, they are not that different. Let's cluster. Okay. So first, like, let's again, we're going to prove this theorem. So let's rescale stuff. Okay. So let's say I've rescaled all the vectors where Gaussian width is now exactly 1. So I have my Gaussian process with many, many vectors whose total width is, whose Gaussian width means the expectation of the soup is 1. I'm trying to find a small set of vectors and real numbers such that the soup is approximated 1 or in expectation, like absolute value of the expectation. I will try to cluster the vectors, and in particular, let's cluster. So what is the metric I should cluster? Well, let me cluster so that I'm forming a small cover of my set of vectors. Okay, that's like the natural thing. So these are my points in space. I form clusters like this. And let's say each of the clusters has width at most 2 delta. Okay. And I just try to cluster using these vectors, okay? This clustering, okay? So I have many, many vectors. I've created a delta covering, and let me call the cluster C1 to Cn. So what am I trying to do? I'm trying to come up with a small set of vectors representing all these vectors. So I should try to obviously, like, take one cluster representative for each of my clusters. Seems like the natural thing to do. Let's do that. So within each cluster, we just choose any particular vector via RS. Okay. So let me just say I choose that one, that one, that one, the ones in the orange. And now to approximate the soup of all my vectors. So now let's focus on one cluster at the moment. I look at the soup of G in a product with V, where V is allowed to be any vector in CS in my cluster number S. I have many, many such clusters, but let's just focus on one. I can say, well, by just breaking this one up, this is G in a product with that particular cluster representative plus soup of V in CS, G in a product with the difference vectors. Okay. Since these vectors, the difference vectors are all at most 2 delta in norm, what can I get from this? Just applying, like, standard tools from the theory of Gaussian processes. What we can get is that the soup, basically, to summarize, the soup of the Gaussian process restricted to just the vectors in the cluster CS is approximated by GVRS. Okay, this Gaussian process corresponding to this one single Gaussian random variable minus CS, where what is CS? Plus CS, where what is CS? CS is the expectation of this soup. Okay, basically, like, if you have a Gaussian process, maybe say it slightly differently. If you have a Gaussian process where every vector has small norm, then it is very tightly concentrated around its expectation. So whatever be its expectation, we just use that as the offset. Because the variance is small, this big Gaussian process in the cluster is approximated by a single non-centered Gaussian. Okay. So now, what should I do? So far we have that in any cluster, I can approximate the Gaussian by a single Gaussian plus sum of set. So now, if I have many, many clusters, I should just say, okay, let me approximate the Gaussian over all my vectors, or Gaussian clusters over all my vectors, as just the soup over all my clusters, the Gaussian over inner product with the representative of that cluster plus the offset of that cluster. Like you have the approximation for each cluster, take the soup over the approximations. Nothing fancy going on there. The question is, okay, how does the error blow up now? I had delta error for each cluster. I have m clusters. How does the error blow up? Okay. You can actually show this that the error blows in a nice manner. It's like delta square root log m. Okay. Basically, this will happen if all the m clusters basically lived in completely different spaces. Okay. So sorry, I'm going to go quickly now. Okay. What is the value of that? Well, because my error is delta square root log m, you can say, well, if m is 2 to the little o 1 over delta square, I'm already done. My error is very small. Great. You say, okay, what if m is super large? Well, actually, can m be really large, like 2 to the omega 1 over delta square? The answer is actually no. If m is 2 to the omega 1 over delta square, that is the best delta covering you can get of the space, requires many, many clusters. You can show that the expected soup is actually going to be super constant. It cannot be 1. Okay, this is, so again, like, I'm trying to say, like, that.
But here you seem to be doing is one, these things are multi-scale approximations typically, right? Why
not even
This is not yet multi-scale. So I'm going to now point out the need for multi-scale approximation. I'm right now doing one scale approximation. The problem is if you do one scale approximation, 2 to the little o 1 over delta square is very good for us. We would be done. 2 to the omega 1 over delta square cannot happen because at any particular delta, it cannot be 2 to the omega 1 over delta square because then the expected soup is really large, which I know is not true because I assumed it's 1 at the beginning. This was just application of pseudo-Cook minoration principle. This, however, leaves open the possibility that m is exactly 2 to the theta 1 over delta square. And in fact, there are Gaussian processes with constant Gaussian width for which every delta, at every scale of delta, the number of clusters you can create is precisely 2 to the theta 1 over delta square. It doesn't matter what delta you choose, is always. So this kind of means that the single clustering strategy is not going to work. And we have to do a clustering at a multi-scale, and this is where Talagrand majorizing measures theorem comes up. Basically, like, Talagrand's majorizing measures theorem, I'm not going to take more of your time. Talagrand's majorizing measures theorem gives us like essentially this multi-scale clustering, which on an average results in like, a certain error being small. That would take some time to describe exactly what happened. But basically, it's not a very hard, once you have the majorizing measures theorem and you exactly see what is the error you're looking at, then the Talagrand's majorizing measure theorem can be used to create this multi-scale clustering, which creates, like, what is the clustering you should choose at various different scales, so as to give you a small set of vectors, constant set of vectors, which shows that the Gaussian process can be sparsifying.
So is the reason you need to use majorization theorem and not just Dudley's, because the majorization theorem actually tells that the best possible error will be.
The Dudley's thing will just tell you that like, at Dudley, there's a weak upper bound. And what we want to say is really the lower bound is the crux here, that we don't really use the two-sided thing.
We want to approximate the E sup x in T.
Yeah.
You want to just use an approximate for the.
Yeah, you basically you want to say, like, doesn't matter, like the precise clustering statement doesn't matter, but the point is we know that the expected soup is 1. So the majorizing measures theorem will tell you that there is a hierarchical clustering here such that the right-hand side is small.
Yeah.
That's like the hard part of Talagrand majorizing measures theorem.
Other side.
And the hard part is telling you like the diameters at various scales of these clusters cannot be very, very large. Like, the certain sum has to be convergent. So it's really the hard side.
Tight side of that. This is the tight side of W.
This is the tight. Yeah.
This
thing. Yeah.
This.
So this is where you have to really use Talagrand's majorizing measures theorem, because that's why we're trying to show this clustering. You start with the assumption that Gaussian width is 1, and you want to show thus the clustering that it created cannot be like super, there is a smart clustering which has the right.
Which actually achieves this.
Which actually achieves this. So this is small also. So So it gives you the right clever clustering, which will give you which even though you could have many clusters at any at any scaling at any scale, but at a multi-scale clustering, the error will definitely go down. So that's sorry. There's like a lot of what's your
Is
name?
it constructive, this clustering?
The in as much as the Talagrand's majorizing measure theorem is constructive.
Yeah, but I don't know if that is like algorithmically, so you give a bunch of points, will you be able to give it a good?
Good. I think so. Randomized algorithms, yes. Randomized algorithms, yeah. Because I think what I think what Talagrand's the proof really does is it will say look at all the what does it do? I think it literally greedily clusters and says, oh, if this all you need is the power to compute the expected soup of Gaussian processes. Other than that, the Talagrand's majorizing measure theorem is completely constructive. Basically, you should have an oracle which, given a set of vectors, would tell you what is the expected soup quickly. That is a simple question. If you want to have a randomized algorithm, you just sample and see what's the expected soup. Deterministically, it's a hardish question, really. But so it is constructive. We are allowing randomized algorithms is all constructive. So yeah, I ran out of time as usual. So thank you. I'm happy to answer the questions.
Questions?
So the DS thing would just correspond to having a fixed schedule, right? Of this cluster's diameter.
Because it will only be the ID part in the other side.
That
But
is
also the schedule is fixed, no? In that
Yeah, at least fixed. I think it's
you just keep 1 by 2 to the n or something.
see you take the covering number at delta divided by powers of 2.
Yeah. I think
yeah,
that's-
But that's not tight. It just says that you can get
give an upper bound.
you get an upper bound of f on this using this, and this is in some strategy of that kind.
yeah,
Will give you a lower bound also.
Yeah.
That's
the part we require, right? And yeah, the upper bound will just as far as this thing is concerned, will give you really nothing really, because we'll just say
covering number never showed up.
I guess you can ask in terms of other question, one can ask if you instead had a Boolean process like a Bernoulli process. Now there are much harder theorems, but true theorems are known there. Does it mean Boolean Bernoulli processes? So every random variable is a Bernoulli rather than Gaussian. There we also exactly know when the width is expected Boolean with Bernoulli width is small. The vectors could be have small L1 norm, or they could be in the Gaussian world. And so tight Latala and somebody else, Berners and Latala is that vectors lie in the Minkowski sum of.
So there's a version of majorization for.
Yeah. So that was a famous question of Talagrand. For which he offered $5,000, which I don't think was enough really for the amount of work it took really to do it. The easier ways to earn $5,000, I assume, proving that kind of theorem. But basically that because Bernoulli random variables, the width corresponding expected width Bernoulli width would be small. If your vectors were just small L1 norm, then of course the Bernoulli inner product of Bernoulli with this is small. Or you could be in the Gaussian world. And basically, the Bernoulli process conjecture now theorem states that is small if and only if the set of vectors is in the Minkowski sum of small L1 norm vectors plus whatever for which the Gaussian thing is small. So you could now try to ask, could you sparsify the Gaussian part in conjunction with the L1 norm part? I don't know. It's like a complex theorem to prove. Latala, Berners and Latala, and one more person.
So it's possible. So if your classification result is tight.
The sparsification result, right? So sparsification.
Depends on W.
Yeah. So let me just look it up. Where the sparsification? It is tight in. It is right. So the in the dependence on the epsilon, it is definitely tight. Is like not tight. Sorry, our dependence is exponential 1 over epsilon, and we show that there's an exponential 1 over square root epsilon necessity. Whereas if you look at the Boolean world, it's log 1 over epsilon was the first answer. So like, we have a triply was dependence on the upper Boolean upper bound, and we know doubly was dependence is necessary. I forget what was the dependence on W. I feel like there was something like, I forget, like we have a doubly exponential dependence on W also. And
The four.
to the W to the 4. And I think 2 to the W is necessary. But that is not qualitatively different from
That was
Bernoulli world. So we're off by like, 1 exponential in both epsilon and W. But epsilon dependence kind of shows like that. Maybe that kind of technique in the Boolean world cannot directly be imported here.
No.
Okay.
Understand.
Yep. Right, switch off the Zoom thing.
Yes. Right.